Hello, we're GRAIC. We did RRT obstacle avoidance and an adaptive control for boundary navigation. This is our final project video. Our goal was to write an autonomous agent to navigate a dynamic track, handle sharp turns, respond to unpredictable obstacles and other agents efficiently, and complete the racetrack as fast as possible. So here's our system workflow. We initialize Carla, set the map to run on, and we call wrapper.py, which will generate scenarios, and call automatic control GRAIC, which every simulation tick will return a control decision from agent.py. And we have three novel methods. We have RRT, A star, and proximity-based trailing strategy. So the trajectory planning is we use boundaries to calculate the curvature and derive speed, and we're going to select a look-ahead point to compute the steering angle and check for obstacles in front. So if there's obstacles, we will run RRT or A star, depending on which method you want to do, and find and adapt a new collision-free path and adjust our steering angle. And if it fails, we will use our proximity-based tracking strategy, which in addition to adjusting the speed to match the car in front, we'll do other things to make sure that we're not colliding, and we'll try to squeeze by if it's possible. And then we issue control commands to the vehicle. So this is method one, which is the dynamic trajectory calculation. And as you can see, it pretty nicely follows the path. Waypoint-based fails because there's not enough waypoints in strong curves, so we overestimate the steering angle. And you can see here it's very accurate. So method two is our curvature-aware speed control and our multi-stage curvature evaluation. This has detailed conditional checks with fine-grained tuning that we did for hyperparameters. Allows for smooth acceleration, deacceleration, and overall stability during the driving. And we evaluate the current and future curvature, and this allows us to have very smooth result that beats all of Jan's baseline results. So you can see here the velocity versus time graphs, and they're very, very smooth compared to other results shown in other projects. So this is method three, which is our obstacle avoidance with the RRT planning. We only run the RRT if the obstacle is in front of the car. It's going to generate a collision-free path, and it's very effective at handling unexpected obstacles along the center line. If there is no valid path, we resort back to our proximity-based method. And here's some of the pseudocode. So it's building out a random tree, and the way it builds it out is it picks the nearest node to the goal point and tries building out random points from there. So here's an example of obstacle avoidance. You can see it encounters an obstacle, and here we will plot the result. And once you have a result, you'll see that it turns green. So it's going to go left around the car. And here is our proximity-based trailing method. And you can see here that it follows the car very nicely and avoids any obstacles, and will try to sometimes go around, as you see there, using the future curvature if it's possible. So it will not always stay behind the car, and with this we got scores way better than Jan's, and very smooth acceleration and deacceleration, and overall a very, very good result. So these are results without this scenario, which is the RRT method. You can see they're all better than the benchmark. And this is with this scenario with the proximity-based trailing method. You can see the scores all better than Jan. Unfortunately, we had one collision in the Shanghai, but that's, there's a whole lot of agents, and it's will take a lot more work to get a perfect result. So thank you very much.